Hello everyone. Today we're going to derive the general solution of a first-order linear non-separable differential equation. And as you move on in studying differential equations, you come to realize that most differential equations you need a kind of trick to solve. And most of the time those tricks that you use aren't necessarily very intuitive because they are just tricks. And the trick that we're going to use to solve this type of equation is called an integrating factor. And that's usually represented by mu of t. So the integrating factor is actually a function. And how we use an integrating factor is just multiplying it by the entire equation. And that will allow us to recognize a relationship between the terms in the equation and solve for mu and eventually solve for x. So these equations take the general form x prime of t plus p of t times x of t is equal to q of t, where x is the function that we're trying to solve for and p and q are just arbitrary functions of t. Okay. So now for solving this, I'm just going to multiply mu by everything in this equation. So we have mu times x prime plus mu times px is equal to mu times q. Okay, so now the relationship that we're looking for is on the left side of the equation. And you might say, hey, this kind of looks like a derivative rule that we've used before, maybe the product rule. And you'd be right, that's a fair assumption. We have the derivative of one function times another function plus that function that we had the derivative of previously times another function. So this is all we can write. We can assume that this is x times mu all prime. So this is the derivative of x times mu. And that means that the derivative of mu, or mu prime, must be mu times p. And now we can solve for mu. This is just a separable differential equation. So separating our variables, dividing both sides by mu, we get mu prime over mu is equal to p. And now we can integrate both sides here. And the integral for p is a function of t, so the integral will be done dt. And the integral of 1 over something is the natural log of that something. So we have the natural log of mu on this side is equal to, we don't know what p is, so we just have to leave it as the integral of p dt. We want the most general form of our solution here. We have the most general form of the equation, and so that doesn't give us a whole lot to work with actually expressing values. So to solve for mu now, we just exponentiate both sides. So we have mu on this side and then e to the integral of p dt. So that is mu, okay? That is the value of our integrating factor, and this is always going to be true for mu. Mu is always going to be equal to e to the integral of p dt. Alright, so plugging that in here, we can rewrite this whole side as just this, but now that we know what mu is, we can write as e to the integral of p dt. And all that is prime, so we have this function times this one, and the derivative of all that. And all that is equal to mu times q. So now we can integrate again across both sides of the equation. And this one will be done dt because these are two functions of t. And I didn't write mu out because it's all that, but just know that that mu is equal to that always from now on. So the integral of a derivative is the function that's inside. That's the fundamental theorem of calculus. So we have x times e to the integral of p dt. And on this side, we don't know what q is, so we're just going to leave that written as an integral as well. So this will be the integral of q times e to the integral of p dt. Okay. So now we're very close to solving for x of t. We just need one more finishing touch here. Dividing both sides by e to the integral of p dt. Okay, so our function, x of t, our general solution to a first-order linear non-separable differential equation, is equal to e to the minus integral of p dt times the integral of q e to the integral of p dt, and then all dt. And that is the general solution.